today's lab, everyone. Today we will do part B of the lab 5, and then we are gonna move on to lab 6 as well. So both of them are small labs, so it's not gonna take that much of a time. Okay, so first thing first, which is lab 5B, and 5B means I said it's gonna be about the maximum power transfer theorem. So it's just nothing, but it's written over here that to obtain maximum external power from a source with a finite internal resistance, the resistance of the load must be equal to the resistance of the source as viewed from its output terminals. Okay, so what does it mean by that? We are going to see in terms of circuit. So when it comes to the circuit, you can see I have a very simple circuit. So if you think about it as a Thevenin circuit, so 11.2 is going to be my Thevenin's voltage, 0.8 ohms is going to be my internal resistance, and then R2, this R2 is my load resistance, right? And this node is my load terminal. So when it says output terminal, that means you have to take a look at from this side. So from this side, the reason the RTH, which is my Thevenin's resistance, you can also say it as an internal resistance to the source, right? The reason why I'm saying that is because I want to relate it to the maximum power transfer theorem. Now, what do I mean by that? Okay, we're going to see the example. So you can see I have R2, and instead of putting a value, I have R in second bracket. Now, why did I do that? Because this is a variable resistance, R potentiometer, okay? And I want to vary the values of it. Now, how do I do that? I want to step through the values of the load resistance. Okay, so in order to do that, what I'm going to do is I'm going to bring up the this command window by clicking this .op option on the top, and what I do is I'm going to go to help me edit and then .step command. Okay, now when I go to .step command, then it asks me the name of the parameter. So what was the parameter inside of second bracket? That's R, right? So linear value, I'm gonna do 0.2, then the stop value is gonna be let's say 2, and then the increment is gonna be 0.2. okay, so you see the step param. So I'm gonna press OK. I'm gonna press it here. Now I have to run the simulation, but it's not gonna run. So when I run the simulation, again the simulation command window opens. Okay, so over here what I'm varying, R, L, so I already put it over here. And now which option do I have to choose? So I'm gonna choose the DC operating point option, because this is just one voltage, right? It's not that we are varying the voltage over here. So I'm gonna select .op over here, and then I'm gonna press OK. And after that, you will see this opens up. So I'm just gonna minimize that. Okay, so the draft tree window, right? So first I'm gonna do is I'm gonna measure the current through it. Comes as that. Sorry. And after I go there, you're gonna see the values. So it's like, in the negative direction. So you already so when I say negative direction, that means the current that's passing through this direction. So if it was like this, I mean the clockwise, then you would have seen the opposite graph, right, which was something like this. So you can already see, just ignore the negative sign. What you do is, like, if you take a look at this portion of the graph, then you're gonna be able to figure out what's the value for which point. So I have a chart ready. So what you're gonna do is you are gonna check the values of the current from 0.2 milliamperes to 1.6 milliamperes. Okay, so you're gonna have to go through this. So when you point the cursor at 0.2, then what's the value? Like, see, you can see the Y, which is minus 11.2. So for your case, make it 11.2. It's just based on the current direction. Okay, so 11.2. Similarly do for 0.4, 0.6, 8, 0.8, 1, 1.2, 1.4, and 1.6, and note down the current. And after that, we're gonna see the graph, what I am trying to mean actually by the maximum power transfer theorem. All right, and like I was saying, you have to take the readings from 0.2 to 1.6. okay, there's a reason why I'm doing that. Your internal resistance is 0.8, so 0.8 has to be there, and apart from that, I took 3 values over here and some values on the either side of 0.8. okay, so I have given an example so you can see, like, I measured the current for 0.2 ohms load resistor, I measured the current was 11.15 milliampere. I got the power as 24.86. Similarly, you are gonna do everything for do the similar readings for 0.4 to 1.6. Okay, and then you are gonna measure the power by using this formula, the power across the load. So when it says output terminal, that means the load terminal. Okay. So here I have written some formulas. As you can see, it's a very simple Ohm's law formula. So the total resistance, this R Thevenin and my R load, both of them are in series, right? And when they're in series, you can add the resistors up, and then whatever the voltage is, if you divide that by the equivalent resistor, then you're gonna get the current, which is over here. Okay. And for maximum power transfer theorem, you have this formula. So power, we know P is equals to VI, or V is equals to IR. That means it's going to turn out to be I square RL. Okay. And when this happens, so actually why am I saying all of these formulas? Because so when is the time you're gonna, what's the value of the load resistor for which you're gonna see the maximum power across the output terminal? Okay. So what happens is, if you see this relation, so the power is directly proportional to RL over here, right? So when I have my RL increased, then my power is gonna increase at the same time. But when you take a look at this equation is also legit, right? So when you have the RL increasing, then you have the IL decreasing, because they are inversely proportional over here. And when IL decreases, so again, if you come back to this equation, you're gonna see that IL is decreasing. That means this is also directly proportional to P max. So P max is gonna decrease as well, right? So it's kind of like contradictory, isn't it? But what happens is, there is gonna be a certain value of the load resistance for which you are gonna get the maximum power across the load terminals. And which is that? Based on the formula, based on the theorem itself, you're going to see that to obtain maximum external power from a source with a finite internal resistance, the resistance of the load must be equal to the resistance of the source as viewed from its output terminals. So what's the internal resistance that I have over here? That is 0.8, which is my Thevenin resistance, right? So when I'm going to have my load resistor equals to the R Thevenin or the internal resistance over here, then I'm gonna get the maximum power. And after I do so this is gonna be the point where I'm getting maximum power. And then if you calculate the power across the load for 1 ohms, for 1.2, 1.4, 1.6, you're gonna see it's decreasing. So in terms, the power is gonna so if you plot, okay, if you plot the graph of RL versus the PL, which is the load's power, then you are gonna see PL going in the Y direction and the RL going in the X direction. You're gonna see the how should I say this? So if you have, so let me just give you a demonstration about this. So if I have a red pen, so if you have PL over here, and if you have RL along X direction, and if you plot these values in the graph, then you are gonna see it is gonna be something like this. And what's gonna be this value? This value is gonna be when RL is equal to RTH. Okay, at that time you are gonna get the maximum power across the load. So if you have got that, then your theorem is verified, and that's how you can actually understand the maximum power transfer theorem when it comes to a circuit. Okay.